ISTA monthly online lecture series. ISTA, many of you know, was founded in 1988 with an aim to promote, encourage, and develop the growth of aerosol science and technology disciplines and their applications in India. In our efforts to promote exchange of knowledge, mainly pertaining to the growth of aerosol science, this monthly lecture series has been an important step. This is our 16th lecture, and if you want to have a look at the previous lectures, we have recorded versions of our previous lectures in our YouTube channel as well as in our website. We recently concluded a very successful workshop on atmospheric aerosol instrumentation, and just to remind you, we are having our yearly conference in December in Dehradun. Now, coming back to this lecture, this topic is interesting as well as relevant. Studies on ultrafine particles are crucial, and the lecture focuses on recent advancement and important aspects in this direction. This lecture is supported by TESCON India, and ISTA thanks them to sponsor the same. I am now excited to give the baton to Dr. Vijay Kanavade to take you forward. He himself has done good work in this field, and he will now introduce our esteemed speaker, Dr. Roy M. Harrison. Dr. Vijay, please.
Thank you, Manish. I hope I'm audible.
Yes, you are.
Perfect.
Yes,
thank you. Thank you once again. Good morning and afternoon, those who are joined from other parts of the world. Okay, it's my really honor to introduce Professor Roy Michael Harrison, one of the leading experts in environmental health and air pollution. Professor Harrison holds the prestigious title of Queen Elizabeth II Birmingham Centenary Professor of Environmental Health at the University of Birmingham, UK. Additionally, he also serves as a distinguished adjunct professor at King Abdulaziz University in Jeddah, Saudi Arabia. Professor Harrison's expertise lies in the field of air pollution with a particular focus on airborne particulates, including ultrafine particles, as mentioned by Manish. In fact, monitoring of indoor and outdoor ultrafine particles has recently been recognized in the European Air Quality Guidelines. His groundbreaking work extends from studying the sources of emissions and their atmospheric physiochemical transformation to assessing human exposure and health impacts, particularly in China, India, and as well as United Kingdom. In addition to his remarkable academic contributions, Professor Harrison is highly regarded for his work at the Science Policy Interface. He has served on numerous technical advisory groups for the UK government, including the Department of Health and the Department of Environment, Food and Rural Affairs, DEFRA, including past membership in DEFRA Science Advisory Council and his ongoing contribution as a member of Air Quality Experts Group and the Committee of Medical Effects of Air Pollutants for the Department of Health and Social Care. Moreover, Professor Harrison has contributed to the World Health Organization's Global Air Quality Guidelines in 2005 and the Guidelines for Indoor Air Quality in 2010. Throughout his distinguished career, Professor Harrison has earned numerous awards, including the John Jayes Medal, the Environment Prize from the Royal Society of Chemistry, and the Fitzroy Prize from the Royal Meteorological Society. Professor Harrison was also appointed Order of the British Empire in the 2004 New Year honors for the services to environmental science and also elected Fellow of the Royal Society in 2017. With over 670 peer-reviewed publications and an H-index of 105, Professor Harrison stands among the world's most cited researchers, as noted by Web of Science. With this brief intro, I now invite Professor Harrison to take over the floor. Over to you, Professor Harrison. Thank you so much for your time, and we are all looking forward to your lecture. Thank you.
Well, thank you very much, Vijay, for that very generous introduction. I'm just setting up the screen sharing and attempting to get into full screen mode.
Yep.
It looks as if it's already advancing the slides for me, which I didn't ask it to do.
Yeah,
Is
now
that
it's
nicely
good.
visible for you?
Yes.
Excellent. Thank you very much. I'll try and arrange a pointer that should make it somewhat clearer, my explanations. Good. Well, thank you very much for this invitation to speak. I'll share with you some fundamental information and some of our research findings relating to ultrafine particles in polluted atmospheres. So my introduction will be largely about just the basic concept of ultrafine particles. And then I'll say something about the primary emission sources, including some of our work on diesel particles, then look into secondary particles formed in the atmosphere, and finally give you a few conclusions on trends and the future. So by ultrafine particles, also widely referred to as nanoparticles, I'm referring to particles with one dimension less than 100 nanometers. They can be separated and measured by mass, but that's very rarely done because they actually represent very small mass and they're not that easy to separate cleanly. But more often, for reasons I'll come to in a moment, we can measure them by number. And this is because when we get to 10 nanometer particles down here, we have 1 billion of them representing the same volume as one 10 micrometer particle. So they're very small, they have very little mass, but they're very numerous and they represent a substantial amount of the surface area of particles in the atmosphere. And this just illustrates it a little more graphically, that for a total mass of one, we would go from one 10 micrometer particle up to 1 million ultrafines at 100 nanometers, and obviously considerably more as we get to smaller sizes. And although the surface area is small, the total surface area per mass is much increased in these nanoparticles. And what's interesting, I think, from a physicochemical perspective, is that for these particles, and we would regard the actual formation process to create a particle at about 1.5 nanometers diameter, at that point, we've still got essentially 100% of molecules in the surface of the particle, which can confer some very special properties. As the particles get small or get larger, even up to 10 nanometers, only as far as that, then only about 20 or 25% of molecules are actually in the surface. Generally, well, we can actually measure right down to these sizes of 1 or 2 nanometers, and we can go smaller than that for molecular clusters. And I'll give some results from that a bit later on. Now, just to make the point about size distributions, these are 3 size distributions, the same aerosol, shown on the top left as number, as surface area in the middle, and as volume at the bottom. What we see is when we express the size distribution in terms of number, that the vast majority of number, and this is typically 80 or 90% of the number of particles, is below 100 nanometers. So by counting particles in the air, even without an upper limit to the size range that we count, we generally get quite a good measure of the ultrafine particle abundance. But with instruments like the scanning mobility particle sizer and other mobility particle sizing systems, we can actually set a cutoff at 100 nanometers and simply count the number below that. And that's a very good measure of the ultrafine particles. Now, if we look at the deposition of particles, and this is percentage deposition as a function of particle size, then we find that the particles in the ultrafine range, so that's in this case shown as 10 to 100 nanometers, we see that there is a very large fraction of deposition in the alveolar region. That's the deep lung. So there's good reason to think that these particles, because they deposit in the deep lung and because they're very small size, may be of exceptional toxicity. But the actual evidence from health studies is still very mixed, and there are no air quality standards that are internationally accepted for ultrafine particles. But not only do they deposit in the deep lung, they can penetrate the tissues there, and there is good evidence that they can circulate in the bloodstream and deposit in some of the internal organs of the body. In fact, I heard an interview on the radio, on the BBC radio this morning, about some new research that's going to be done on the penetration of ultrafine particles via the olfactory bulb into the brain and the possible implications for diseases like Alzheimer's. So the WHO, in its 2021 revision to the guidelines, did not set a guideline for ultrafine particles, but came up with a good practice statement, which recommends much more quantification of ultrafines as particle number concentration, that monitoring should be extended and there should be more characterization of ultrafine particles. And it also gave a recommendation for what could be regarded as a low concentration and 2 recommendations for what could be regarded as high concentrations. So they did express concern, but could not actually come up with a guideline explicitly. So what are the main sources? Well, we have primary emissions, and these are largely from the combustion of fuels, mainly fossil fuels, but also other high temperature sources. And I'll say something about road traffic, shipping and aviation in a moment. For most of us living in cities, road traffic is likely to be the biggest source. But also secondary formation in the air is very important. And I'll also be saying something about that as we proceed through the talk. So this is a now somewhat dated inventory, but it gives a good indication of what the main sources were in Europe in 2005. And we see that the transport sector contributes about 75% of particle number emissions. And this biggest share here, 43%, is actually international shipping. And then road transport, and this is the diesel fraction in the brown, is the second major source. Gasoline vehicles are a considerably smaller source, and also I think it's controversial actually how big a source liquefied petroleum gas and liquefied natural gas are as a source. They certainly are a source, but probably not nearly as important as the diesel source. And this is industry, and then we've got a number of minor sources such as residential coal combustion and so on. So it's largely associated at that point with transport emissions. And I always think of this as a rather nice diagram. This is Europe. Scandinavia is up the top here, United Kingdom over here. But what we see so very clearly are the shipping routes around Spain and into the Mediterranean, the road transport routes through the heavily populated countries of Western and Central Europe, and the main cities. The one over here actually is Moscow. But we see clearly London, Paris, and so on. And this is the two main sources showing up, which obviously is the shipping for these shipping lanes, and the major highways are the diesel traffic. Now, the projection in 2005 was that there would be a big fall in emissions by 2020, and that's mainly associated with a reduction in shipping emissions in Europe because of the requirements now for low sulfur fuels, and that has actually been very effective. We don't expect to see any particular improvement beyond that to 2030, and indeed I think the emission in this projection were going up slightly. I think there's some reason to think they may come down because of the increasing market penetration of battery electric vehicles, which particularly by replacing diesels, will give some reduction in emissions of the ultrafine fraction. So we also have secondary particle formation and homogeneous nucleation to form new particles from gases. It has a high energy barrier and therefore requires very high supersaturations. And there are few molecules that are able to form new particles in the atmosphere. But the one which turns out to be important in most contexts, and certainly in the urban context, is sulfuric acid, usually formed from atmospheric oxidation of sulfur dioxide. And that is involved in binary processes with amines or ammonia, as we'll see in an example later on, to form new particles. And those are about 1 to 2 nanometers in diameter when they're formed. And their subsequent growth generally involves the condensation of oxidized organic compounds predominantly. And we'll see an example of that later. But the importance of these two sources of road traffic and secondary formation is illustrated by the data in these graphs. And what we're seeing is the number of particles, so the abundance of ultrafines on the y-axis and the hour of the day on the left, on the x-axis. And this is North Kensington in London, and what we're seeing is the black line is black carbon, and we see the particle number concentration broadly following the black carbon. And that's because at the time of these measurements, diesel traffic was the main source both of black carbon and the ultrafine particles. But if we go to southern Europe and we go to Barcelona in Spain or Huelva, which is in the south of Spain, we see this additional peak in the middle of the day, which is not related to the black carbon, very, very clear in Huelva. And that is photochemical reactions causing secondary formation. And the contribution of that varies very much between the cities, but it is very, very important in some parts of the world, and particularly in those with high sunshine intensities. We have here the total number count as a function of hour of the day in North Kensington, which is the blue, which is a background site within London, so it's urban background, and Marylebone Road in London, where we see this response to road traffic. We see a morning rush hour, we see a build-up of particles in the evening, and a drop in the early hours of the morning when there is very low traffic densities. Beijing shows a strong influence of photochemistry. So even in the very polluted atmosphere of Beijing, there is formation of ultrafines, but also we see an evening peak, which is probably more related to road traffic. But it's largely a gasoline vehicle fleet in Beijing. And the diesels only come in the evening, which is likely responsible for this early evening peak. whereas Delhi shows very high concentrations, no obvious photochemical peak, and the work that we did in Delhi didn't see any clear formation of secondary ultrafine particles. But there's very clear morning rush hour, and then when the diesels come in the city later on during the evening, there's a big increase in particle number count in our data from Delhi. So diesels are very important, and we've done a lot of work on diesel exhaust. There are two main types of particle in diesel exhaust. So there are those with a graphite core, often coated with organic matter, and the primary spheral size there, so the size of the smallest units, which do aggregate and form chains and clusters, but the smallest are about 40 to 50 nanometers. But a larger number of particles are formed by nucleation of semi-volatile material as the hot exhaust gas plume mixes with ambient air. So they're not actually solid particles, they're mostly made up of condensate. And this is because of partition between the condensed phase and vapor for semi-volatile compounds at ambient temperatures. And this process of equilibrium or near equilibrium between the condensed phase and the vapor is responsible for formation of these particles. So what we have is a hot exhaust gas with high vapor concentrations, which mix with cold air. And that reduction in temperature leads to formation of particles because the saturation vapor pressure drops as the temperature drops. Now, as those particles advect away from source, we see evidence that there's some re-evaporation. But those vapors that are generated through that re-evaporation oxidize and form secondary particles, which is a very important process in the atmosphere. So there's a lot to research there, and we were interested in primarily those first three boxes there. And so this just illustrates, if this is the tailpipe and then time after emission on this axis, temperature will fall fairly rapidly as the hot exhaust gases mix with ambient air. And initially, the saturation vapor pressure is below, is below the ambient vapor pressure. And you don't actually get you begin to get particle formation. But subsequently, as there is further dilution, so the ambient vapor pressure reduces by dilution and becomes below the saturation vapor pressure, and the particles will tend to evaporate. So we have two processes. But in street air, we're seeing predominantly this particle formation process. So what's the chemical composition of diesel particles? Well, we've worked extensively in engine laboratory, taking samples from controlled engine operating conditions and analyzing them by two-dimensional gas chromatography. I won't go into the technique, but this is a technique that allows us to separate, really with high efficiency, the compounds within the emissions. And within them, we see essentially two components. You can see in the graph here, diesel fuel contains hydrocarbons up to about C20, and there's a significant amount there. But also lubricating oil is vaporized in the engine, and this creates this second set of peaks from about C18 to C36 of condensed engine oil. And in fact, when we look at the composition of that, this is the carbon number, and this is the mass contribution. The biggest contribution is the blue here, which is alkanes. And then the next is cyclic alkanes, monocyclic and bicyclic, tricyclic. Then monocyclic aromatics. And finally, we see some oxygenates and furanones in there. But the biggest single component is alkanes. And in fact, we've modeled the behavior of particles using alkanes as a surrogate for the volatility distribution. So characterization of the engine emissions was carried out in collaboration with our mechanical engineers using their engine laboratory. And we found, this was a finding initially that we made many years ago, was that the particle size distribution is dilution ratio dependent. And in fact, much of the data published at the time was based on measurements of very dilution ratios, which lead to larger particles. High dilution ratios are more representative of the atmosphere and show both a bigger number of particles and a smaller number mode diameter. And this is because of a competition for condensation on the existing and larger particles and the formation of new and much smaller particles. And that is determined, the outcome of that competition is determined by the dilution ratio. So when we made street air measurements, and this is now many years ago in Marylebone Road in London, we found modal modes in the distribution between about 26 nanometers and 32 nanometers, depending on the time of the day. And this is weekday measurements expressing here the diameter in nanometers and here the abundance in incremental number per increment in log diameter. So a large proportion of the particles are actually smaller than the size of the primary spherules in the solid graphitic particles, which is somewhere up here at about 50 nanometers or so. Remembering, of course, that's a log axis. So when we looked at the ratio of the smaller particles, and these are the ones likely formed by these condensation processes of semi-volatile vapors, to the number of larger particles as a function, so this is the ratio, this is as a function of temperature, we see that as the temperature falls, so as the temperature rises, moving in this direction as the temperature rises, we see relatively fewer of the very small particles. As the temperature falls, favoring the condensation process, so we see a bigger ratio of these nanoparticles to the larger particles. And perhaps counterintuitively, when we look at the relationship to wind speed, and this is wind speed here plotted as knots, the ratio increases as wind speed increases. And that's because the dilution is increased, and that favors formation of these new nanoparticles by condensation rather than vapors condensing on existing coarser particles. So a low volatility vapor can form new particles by nucleation. I think it's actually probably, I've said homogeneous there, I think it's probably heterogeneous on very tiny fragments of metallic ash or of sulfuric acid. Or they can condense on pre-existing particle surfaces. And the high dilution favors new particle formation, as do low temperatures. So it's clear that the factors there that influence particle size distributions and number concentrations in engine exhaust in the laboratory operate also during dilution in the atmosphere. And substantial particle formation occurs during the mixing of engine exhaust plumes with ambient air. Now, in a study in central London, using these various sites for measurements, and we're particularly interested in the relationship between Marylebone and Regent's Park. Marylebone Road is a very busy street canyon, but frequently downwind of it, Regent's Park is a relatively well, it's a background area. I won't say it's clean air because it gets air from all over London, but it represents the urban background close to Marylebone Road. We also made measurements on the elevated BT Tower up near the top of the tower at, I think, about 150 meters. And what we found, and here we've got particle abundance on this axis and diameter here, we found this typical distribution with a mode in the 20 to 30 nanometer region in Marylebone Road. But in the park, that mode has shifted to very much smaller diameters. And on the BT Tower, it's essentially disappeared. And what we're seeing here is very much the solid graphitic particles and probably some secondary particles in the region above 100 nanometers. So what we inferred from that, and we did a number of other studies looking at the rate of change, was that the particles here are shrinking as they are advected into Regent's Park. So in this initial phase, they actually get smaller. They can subsequently grow by condensation of oxidized organic vapors. So it doesn't guarantee that they actually stay necessarily that much smaller. So the hot exhaust gases contain high concentration of semi-volatile components. They mix with cold ambient air. Semi-volatiles condense to form new particles. They're transported away from the road. And because the concentrations of the vapor phase decrease, there will be evaporation and the particles become smaller. Now, we had to make a new laboratory measurements of vapor pressures in order to model those processes in the atmosphere. And we developed this model. The arrows show Marylebone Road along here and Regent's University here, which was the sampling site in Regent's Park. And then we see how on the various time steps in this large eddy simulation model, we predict the evaporation of the particles. So I'm just checking on the time. I don't want to overrun. I hope we won't. Now, we've also looked at the situation at Heathrow Airport. And at Heathrow Airport, the two runways run more or less west-east and east-west. And we've analysed data from the LHR2 site, which is within the security perimeter of the airport and is just north of the northern runway, and from Oaks Road, which is just outside the airport perimeter to the south of the runways. And what one finds is that this is the particle number count, this is time along here. You get an elevation in particle number, and these pretty large numbers, at Oaks Road, for example, the southern site. But when you have that, you don't see any elevation at LHR2. But when you have an elevation at LHR2, you see much lower concentrations of particles at Oaks Road. So what we're seeing is clearly a source within the airport, and just to remind you of the map there with LHR2 and Oaks Road. If we plot a polar plot for LHR2 up here, it's clearly picking up the signal from the emissions of the aircraft on the runway to the south of it, and at Oaks Road is picking up the signal from the runways to the north of it. And when we look at the number size distributions, these are our roads. So this is actually Chilbolton, which is a background rural site in southern England. This is North Kensington, background site in London. This Marylebone Road, highly polluted London site. But these are the two sites at Heathrow, and we see this very small mode at around 20 nanometers, very high concentrations. So airports are a major source of ultrafine particle emissions. And when we actually analyze the plumes from individual aircraft, and these are the aircraft type down here, and worked out an emission factor, and this is the log of particle number emissions per second per passenger. So we normalized it by the number of passengers that the aircraft take. You see clearly there are much higher emissions from departing aircraft than arriving aircraft, but that in terms of the different aircraft types, there are really, allowing for the fact this is a log scale, there are really quite significant differences between the different aircraft types listed down here in terms of their particle emissions. Now, secondary particles, we've looked at particle formation processes as diverse as Beijing and the Antarctic Peninsula. And actually, there's a lot of similar chemistry going on there in the two places, perhaps surprisingly so. And what is happening here is that clusters are forming from sulfuric acid, and primarily sulfuric acid and amines. Now, HOMs are highly oxidized organic molecules which form from oxidation of VOCs, and they can also participate, but their main role is actually after the formation of the sulfuric acid amine cluster in condensing on these new particles which form from the cluster and making them grow up to CCN sizes. So we need SO2 through sulfuric acid. We need amines, or possibly in some environments ammonia, but amines seem to work much better to form clusters which then grow by oxidation of the oxidized organic matter. And we can monitor that by time of flight mass spectrometry of the vapor phase component using an aerosol atmospheric, well, sorry, not an aerosol mass spectrometer, using an atmospheric pressure inlet time of flight mass spectrometer. We actually measure the vapors by looking at the mass defect, which is the accurate mass of an ion minus the integer mass, and looking at that as a function of mass, we get a nice plot here. And this is a particularly nice example from a period of high sunshine. We see this succession of green dots representing ions that we measure, and these represent clusters of amines and sulfates. And this is the growth process as they're growing in mass with condensation of further amines and sulfuric acid into them. This is the peak corresponding to sulfuric acid itself. And we also see a sulfuric acid dimer down here. So when we start looking at the growth of particles, again, there's a mass defect plot, but we can identify what the condensing molecules are, and we can see whether they're ultra low volatility compounds, extremely low or low volatility or semi-volatile and so on. And generally, as the mass increases, so the more volatile constituents condense. Down at this end, we're looking at those initial clusters plus things like the very low volatility species condensing. So we can measure all of those with our mass spectrometer instruments. And in LifeSig, we compared particle size distributions at a roadside site, which is this one, and an urban background site, Tropos, which is this one. And we see that on average, so this is diameter, this is hour of day here, and the color chart represents the particle number concentration. This is a simulation of the banana, as it's called, representing the growth of new particles. We see that there is a more rapid growth to bigger sizes at the roadside site than at the urban background site. And we're also able to look at growth rate contributions of different molecules at the two sites. And what is very clear is that at roadside, we get the more rapid growth, and that appears to be because both of direct emission and formation of these highly oxidized organic compounds that contribute to particle growth. So vehicle emissions, road vehicle emissions, actually favor new particle growth, formation and growth in the atmosphere. And here we've just broken down particles into different size categories and shown how these different groups of compounds, different volatility sets of compounds contribute to growth at the two sites. So in fact, it involves the growth right up to including semi-volatile compounds in the growth ultimately. So those are of significant vapor pressure. And it's very hard to find data on the chemical composition of ultrafine particles. But just going back to some work from a paper by Glenn Cass that he gave in a conference that I co-organized many, many years ago. These are two sites in California where the Cass group made measurements, and they found the predominant component was organic compounds, which fits with this oxidation process and the condensation contributing to formation of ultrafine particles, but also sulfate and the role of sulfuric acid in the core of the particles. So just my final section before conclusions is some thoughts on trends. And I'm going to show you some data from the Marylebone Road Street Canyon. And what's important to note is that with a wind coming from the left-hand side of the plot, there is a vortex driven in the canyon. And on one side of the canyon, a monitoring site measures very largely the emissions from the vehicles on the road within the canyon. And on the other side, on the other side of the canyon, it's measuring largely entrained air coming from the background within the city. And we see that in the pollution loadings here for NO2, for example. And it's worth bearing that in mind in looking at the next plot. So we looked at trends in particle number from 2010 up to 2021. So this is particle number concentration in the nucleation range. And this is the wind direction that gives us the contribution from the vehicles on the road there on top of the urban background. This is the urban background on the left. And what we see is, with the exception of the early years, we've actually seen very little change in the nucleation particle concentration, whereas the larger Aitken mode and the accumulation mode of more than 100 nanometers have shown big reductions. And this is perhaps surprising that we see one type of the larger particles reducing fast and the intermediate, but the smallest don't seem to have changed significantly at all. And in fact, if we plot here the black carbon, which is largely in that accumulation mode of slightly larger particles, the black carbon falls very fast from 2013 down to 2021. And that's attributable to the use of particle filters on diesel exhaust, whereas and similarly, the accumulation mode particles fell quite heavily. And that fall in black carbon corresponds to vehicles that didn't meet the Euro 6 standard and didn't have those particle filters. So what's pretty clear is that the particle filters are removing the larger particles, but they're not removing the semi-volatile particles, because vapors are penetrating the particle filters and then condensing to form those nanoparticles. So we still have a problem with the very small particles, and we see it in the size distribution changes as well on the edge of major highways. Now, the next slide shows some work that we did, a modeling study that we did in Beijing. These are not my data, but this is data from a publication in PNAS. And this shows in terms of particle number, a so-called banana when there's new particle formation. But this continues over several days with particle growth following this dotted line here. And this actually represents a formation of haze, as the Chinese call it, in Beijing. And particle mass concentration, which is the black line, goes from probably less than 10 micrograms per cubic meter, up to about 350 or so micrograms per cubic meter. And this represents the chemical components of it indicated here. And what it appears is happening is that this event of forming nanoparticles, although it doesn't make much mass, you see the mass doesn't really change, it provides a medium for the oxidation of gases, which then goes to form a huge amount of particulate matter. So the growth of new particles normally attributed to the condensation of sulfuric acid and highly oxidized molecules. And if you calculate growth rates from that, you find that they're far lower than those actually observed in the Beijing atmosphere. So traditional growth mechanisms can't explain observed particle growth rates and account for only about 10 micrograms per cubic meter of mass, whereas the production of something like 100 micrograms per cubic meter or more can only be explained by uptake of higher vapor pressure species and heterogeneous chemistry. So new particle formation and ultrafine particles are a crucial contributor to particulate matter mass in Beijing, which is a finding from Marco Kuhlmüller's group, not ours. So just to summarize some future prospects, a reduction in the sulfur content of fuels is leading to reduced primary emissions from combustion sources. The sulfur reductions are also leading to reduced particle formation by homogeneous nucleation, which is what we were able to model in the data from Beijing. Diesel particle filters are highly effective in removing solid carbon nanoparticles, but far less so in controlling the particles formed from condensation of semi-volatile hydrocarbons. And we've learnt a huge amount from new instrumentation and theoretical advances in aerosol science. But as yet, we know little about the emissions and health risks of engineered nanomaterials. So these are acknowledgements to just a few of my many co-workers and collaborators, but those who've done most of the work behind those slides and the funders. And with that, I'll thank you very much for your attention. So I'm more than happy to take questions.
Yeah.
Would you like me to stop screen sharing, or shall I leave it there in case?
Maybe you can leave for some time if somebody want to go to a particular slide.
Okay, I'll leave it there.
Okay.
Happy
First of all,
to
thank
take
you so
questions.
much for such a nice, wonderful, enlightening talk. I'm sure there will be many questions, so I request audience to please raise your hand, and I will ask you to ask question one by one. And if somebody has any problem, he or she can type in the chat box also. Please raise your hand. Okay, while people are, yeah.
Hi, Neeraj. This is Vijay. Sorry.
Yes, Vijay, please continue.
Can I go ahead?
Yeah, please continue.
I was just trying to figure out how to raise a hand. It looks like I forgot. No, I couldn't find the tab, but that's okay. I actually posted question in chat, but let me read out for you. How difficult is to disentangle primary and secondary production of aerosols, qualitatively or quantitatively? And although UFPs have insignificant contribution to the total aerosol mass, but effectively whatever emitted to the atmosphere will likely to grow by vapor condensation in the atmosphere. So in a sense, nothing is primary, nothing is pure in the atmosphere. So what is your comment on this?
Well, you make a very good point that because of the condensation process, which occurs on both primary and secondary particles, many of the, particularly the larger particles in the atmosphere are mixed
Yes.
with primary origin, but a secondary coating on them. So we shouldn't make the distinction too closely, especially for the larger particles. But it's certainly, in terms of the very small ones, it's useful to try and make the distinction as to whether they're emitted. What makes it even more complicated, though, is that the smaller mode in the diesel particles, and this applies to some other combustion sources as well, is essentially secondary, but we refer to it as delayed primary because it's just particles that are from an emission source, but they're formed more slowly. So we should regard them as primary. But it's actually in terms of, for example, particle size distributions and the application of receptor modeling techniques like PMF to size distributions, it's very difficult to clearly distinguish the primary from the secondary. And in fact, we're working on enhanced PMF methods to try and tell the difference between particles in the nucleation mode, so we'd regard that as probably smaller than 30 nanometers, that have come from road traffic and those that have come from secondary formation processes. It really is quite difficult to tell the difference.
Thank you. Thank you very much.
Okay. So anyone else want to ask? He can or she can ask directly, because if there is any problem in raising hand. Yeah, anyone else? Otherwise, I will read out from the chat box. Anyone? I also have some question, but that I will put myself at the last. So okay, so let me read out the question from chat box. There is a student named Yash Dahima. He's trying to understand. He's asking that, do you foresee ultrafine particles being regulated independently of PM 2.5 and PM 10 in near future? What are the key scientific gaps that need to be addressed to facilitate more targeted regulations?
Yeah, that's also a very good question. It's one I get asked quite frequently. I think it likely that by the time of the next WHO revision to the air quality guidelines, that there will be a guideline for ultrafine particles. What has delayed that is that there has been a relatively small number of epidemiological studies concerned with ultrafines, but that situation is progressively changing as more studies are done. And also that those studies that have been carried out have looked at different health endpoints, have used different metrics for ultrafines, and whereas the guideline for PM 2.5, for example, was set on the basis of a meta-analysis of relatively similar studies done in different places. The database just hasn't existed to do that for ultrafines. So without that meta-analysis or at least one very authoritative study, we've not been in a position to determine exposure response relationships. And it's only when you've got those exposure response relationships that you can quantify the impacts and that you can realistically go into the standard setting process. So I think the WHO was quite right to decide that it didn't have sufficient information. But I think that information base is growing, and hopefully by the time of the next revisions, which probably another 10 years or so, we should have ample data to do a meta-analysis and to set an appropriate guideline for UFP. But don't expect it very soon.
Okay. So another question is, can you explain in brief about the projection of vehicle-induced ultrafine particles? And please brief about engineered nanoparticles. That is in the chat box. Yeah.
Yes, this subject was quite controversial in the UK about 10 years ago, that there were projections of massive industrial production of engineered nanomaterials. And I don't think it's ever actually materialized that there has been a growth in manufacturing nanomaterials, and they do have some very real uses. But I think a lot of the projected uses didn't actually turn out to be commercially very viable. So the expansion of the industrial production hasn't occurred as rapidly as was expected at that time. But undoubtedly, there are facilities, well, there have been historically, for example, titanium dioxide for use in paints, or compounds like zinc oxide, which are used as nanoparticles in sunscreens, for example. They are produced in quite large industrial quantities, but their usage doesn't actually disperse them into the atmosphere. So I think with good control of manufactured processes and attention to the way in which nanomaterials are used in products, I don't foresee very much dispersion into the atmosphere, and therefore I think this is not going to be a big vector for exposure. I think it's still going to be largely the combustion generated and the secondary formed ultrafines, which are responsible for most of the human exposure. There will be some engineered nanomaterials there without a doubt, but I don't foresee them being there in large concentrations, unless there's, for example, an accident at a production facility. But time will tell. I may be proved wrong, but that's my current understanding of the situation.
So let me ask another question. Can I ask 3 more questions? Do we have some minute time, Professor Harrison? Can
Oh,
we
I
take
have
some?
time. If you wish to go ahead, yes, please do.
Okay, so another question is the chat box. It asks, will it make sense to include emission norms for ultrafine particles in the context of in-use diesel vehicles? I think he's trying to ask whether means when diesel vehicle is running, that time is whether ultrafine, how much ultrafine particle people are exposed to or something similar. That is what probably I'm.
So I'm still not quite clear what the question.
Let me repeat what he wrote. So will it make sense to include emissions norms for UFPs in the context of in-use diesel vehicle? Probably he is trying to understand whether means when diesel vehicle is moving, so that time whatever emissions are coming from ultrafine particles, so do we need to make emission norms for that? How many particles you are emitting when diesel vehicle is running?
Well, there are emission standards in Europe for ultrafine particles from road vehicles. So the number concentration above 23 nanometers is regulated on both gasoline and diesel vehicles, because gasoline direct injection vehicles are a source of ultrafines. So there is a limit on emissions already for those vehicles, and under the air quality, the emissions directive, which is to be revised for Euro 7. There's a draft directive available. I think that's likely to be approved quite soon. They'll require measurements of involatile particles down to 10 nanometers, as opposed to the current measurement of involatile particles down to 23 nanometers. But what they don't regulate is the delayed primary particles, those forming from the vapor condensation. And that was a recommendation from a working group because of the difficulty of measuring them repeatably. And given that they are dilution ratio dependent, it's very difficult to get really repeatable measurements on a test bed of those particles. And because they are formed as they dilute with ambient air, you couldn't actually make real driving on the road measurements of them. Whereas you can measure NOx in vehicle exhaust gases as you drive along, you can't measure ultrafine particles without ignoring the delayed primary particles, which actually form after the emission from the exhaust.
Probably he asked because in India we measure carbon monoxide and NOx, CO and NOx, to see whether vehicle is polluting or not. So we have to get some PUC certificate, and there we use only CO and NOx. So probably that is the reason he was asking. So another question is by a PhD student, Ms. Swati Joshi, and she is asking, as we are moving towards improvisation of fuels and more towards electric vehicles, so that means ultrafine emission from combustion of fuels will be less, but it is found that the braking system and tire wear also produces nanoparticles. So what are your views on it?
Yes, there's a fair amount of research going on in this area at the moment. The conclusion I would draw from research to date is that under most normal operating conditions, the emissions of ultrafine particles from tire wear and brake wear are quite small. The number concentrations they generate are small. If, however, the brakes get very hot, and if there is a lot of friction on the tires from, for example, wheel spin or very heavy cornering, then you do get an emission of more significant levels of ultrafine particles. But during normal operation, the emissions are quite small, and there's quite a lot of work that shows that. But there are, certainly for brake wear, there are recognized threshold temperatures above which you do start to see, I think through initial formation of vapor and then condensation, you do tend to see quite high concentrations of ultrafines generating, but they're not temperatures that are usually generated during normal driving. They're only during very, very heavy braking.
Okay. Now let me add my question. So you were talking about the ultrafine particle composition, and there you said about 50 to 60% is organic, and then quite a bit of sulfate, and then metal oxide was also quite significant. So when we talk about metal oxide, so is it only from the high temperature combustion process, or there are some other natural sources of metal oxide in the atmosphere?
I think they're going to be almost all high temperature processes of some sort for the particles to be in the nanoparticle range. There will be very few arising from things like natural mineralization or from formation of marine aerosol or that kind of process, which largely generates coarse particles. So I think they're mainly from high temperature sources, fuels which contain metallic impurities, metallurgical processes carried out at high temperatures, which are well recognized to emit very small particles. Those are likely to be the main sources of ultrafine metals in the atmosphere. We did publish a review of measurements now quite a few years ago, but it wasn't entirely clear what the sources are, but that would be my intuition that they are very largely from those sorts of high temperature processes and combustion of fuels containing impurities, including coal, of course, which contains a large amount of metal impurities. If they're not trapped in any abatement equipment, there will be emissions of trace metals from coal combustion as well as fuel oil, automotive fuels, and so on. They're all likely to be sources if they or certainly the liquid fuels, not the gaseous fuels. They'll be pretty clean.
And one more thing, this is just a query. You were showing a plot where mass effect versus mass to charge ratio.
Yes.
And then you were showing this for different volatility. So VOC, IVOC, SVOC, LVOC, and so on. So I was just trying to understand this. How do you define the different volatility? So what is the criteria you take to define that? Okay, this is you will call SVOC, then LVOC, then ELVOC, then ULVOC, and like that.
Right. Well, there are well-recognized protocols for determining the boundaries between those groups. So they're recognized boundaries. They come largely from the work of people like Neil Donoghue at Carnegie Mellon, who was the first person to propose the volatility basis set for modeling the behavior of compounds. So if we know a molecular formula, which we can get from the mass spectrometry, then there are algorithms that will calculate a vapor pressure, and then there are accepted ranges of vapor pressure corresponding to those different categories of particles. So these are recognized boundaries that we take from earlier work from the literature.
And one last question from my side. You were talking about the measurement over this Merrill-Bohn road, and there you would have shown that effect of temperature. And effect of temperature, you have shown it was as high temperature means you have less of ultrafine particle. But if the way I was seeing, I could see there was a bimodal kind of distribution. If you can go to that side, means I've seen that there is an increase, then decrease, and then again it is effect of temperature you were showing. Yes, here. So here, if you see from 0 to about 12 degree, there is a kind of hump. And then again from 12 to 27, it is again. So what is your thought about? What are your thoughts?
I think it's noise in the data.
Okay.
I don't think there are different processes that are being reflected there. I think it's noise in the data. There are other studies that other people have carried out which have shown this temperature effect, particularly in Scandinavia, where they tend to have a bigger range of temperatures that we do. They've similarly shown an enhancement of particle number concentration at the reduced temperatures. So I think that's the main effect. You're quite right. There could be some other effects in there causing that apparently bimodal behavior, but I do think it's probably just noise in our data.
Thank you so much. So now, if you then there are two questions in chat. If you allow, I will ask. Otherwise, we can stop. So, what do you say?
Yes, okay.
Okay. So there is a student Shivansh. He's asking, why are diesel particle filter less effective in controlling particle form from the condensation of semi-volatile hydrocarbons?
Well, remember this is a delayed formation process, and what is happening is that vapor from unburnt fuel and from volatilized engine oil is able to pass through a filter, and so the diesel particle filter is not collecting those semi-volatile vapors. And as they cool after emission, they'll form the ultrafine particle fraction. And that's why it would seem that the diesel particle filters that have worked very effectively on the accumulation mode particles and the black carbon have not controlled that nucleation mode in the size distribution emitted from diesels.
Oh. And this is the last question. And she is another student, Jayashri. She's asking, does ultrafine particle enhance CCN concentration in presence of sulfuric acid or alkylamines? So she's asking if CCN is sulfuric acid or if CCN is alkylamine, which one would be better in terms of CCN? That is what probably she's trying to ask.
So sulfuric acid or what?
And alkylamines.
Oh, alkylamines. I don't think I have an answer to that. The cluster formation in most locations that have been studied is dependent on a combination of sulfuric acid and amines, but there's not been a lot of experimental work that would show normally the amines are in lower concentration. So the process is probably more sensitive to the amines, but actually getting to CCN size, the highly oxidized organics are very important because of the condensation process. So probably the sulfuric acid and the amines are largely responsible for determining the actual number concentration, but the growth to CCN size is much more dependent on the oxidation of the VOCs. So I'll sort of dodge the question slightly by giving that as an answer. So I hope that gives enough information to think about it further.
Yeah. Thank you so much. Okay, now we are coming to the last part of this session. That is vote of thanks. So first of all, I wish to thank on behalf of ASTA and on my behalf, Professor Roy Harrison, for accepting my invitation. And in spite of his busy schedule, he took out time and he gave us such a wonderful lecture. So thank you so much, sir. I would also like to thank Dr. Vijay Kanavade for introducing the speaker and the BARC team. BARC is Bhabha Atomic Research Center. that team who is managing this, who is handling this, this online platform and making all the kind of things. And most importantly, the audience for which we are doing all these things. And since you are coming, so that is why we are trying to call more and more speakers to continue this series. So with this, I wish to thank everyone, and we will come again with some another good lecture with other speaker. Thank you so much. Thank you, Professor Harrison.
Well, thank you very much, Dr. Rastogi, and enjoy your evening. Thank you.
Thank you. Have a nice day. Yeah.
Thank you, Neeraj. Thank you, Professor Harrison. Bye-bye.